Alright, and we're in action. Cool. Dun, 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 dun. Oh no. Alright, we're gonna stop the music for a second. Check, check, check. I don't want interference. I want to change it from the... Whatever, we're just gonna roll with it, man. We're just gonna roll with it. Alright, hold on. Alright. Everybody chill. Alright, I fucked up. Bang, we're back on it. We're back on it. So, continuing where we left off, let's get back into it. So, I'm gonna attempt to follow this other brother's method, alright? So, we're gonna work with this. Maybe the music's a bit loud. Let me turn it down just a little bit. Right. Alright. Basic oscillator design. Alright, let's think about this from an abstract level. I want to do this from the very beginning so that I fully understand it, okay? Even though it's like it's a simplification of the whole ordeal at this moment, but right, yeah, let's understand this in the sense of what A means and what beta means, because yeah, that's a fine distinction. Beta is more like a box. And feedback. Okay, something like that. Yo, it's too bright. Nah, that's better. There it is. Okay. Indeed. Now we have a realistic amplifier model. That's not very good. I've seen this before. No more. Feedback. Bang. Hey, whenever you want. Beta. V1. R out. R in. Yeah. V2. Okay. Alright, bet. Oscillator based design, amplifier feedback. Which we take a simplification. Yeah. Okay. Alright, and this is what we got here. Okay. Oops. Oh shit. That's all in view. Alright, cool. Real second model. That's right there. Centered up. Centered up. Centered up. Centered up. Okay. Moving moves. Yeah, they're around. Bang. Bang. Yeah, go like. You know, then we'd cut that out. That's what I'm trying to say. So it'd be like a joint, and then, you know, snip. Whoops, I did the wrong snip. You know, and then snip, snip. You know what I mean? Snip, snip. Alright. Very well. Very well, very well, very well. Okay. Alright, then we start analyzing V1 over V2. V1 over V2. For the purpose of solving for what? Where are we even at right now? Okay. Z1, Z3, Z2. Alright. Nail those correspondence. Alright. Yeah. A1, V1. V1. There we go. Alright, and our dependent voltage source. A1, V1. Sure, but this is our... I mean, we're doing coal pits with an NPN bipolar junction transistor, you know what I mean? So, why are we first looking at the voltage gain rather than the current gain? Bro, man, I need some water. Oh man, stops every time. Alright, we get into the sauce of it. Yeah, get into the sauce of it. Z3, Z2, indeed. Z2, A1, V1. A1, V1. Okay, A1, V1, E1, V1. V1 over V2. V1 divided by V2. Let's look at the differences between these two positions. This is V1, A1, V1, V2, V1. These two. Divided by Rn divided by plus V3. V1 over V2. Voltage V2 to voltage A1 times V1 are parallel circuit elements. Indeed. Okay. And this is Rn parallel Z1 divided by Rn Z1 plus Z3. Indeed, so it's setting up the series. Okay. Nice, very fun. That's very good. So indeed. Alright. We're solving for this ratio. Interesting. Okay. Alright, so this is V1 equal.
My name is Bob Fudge. I was born in Texas. Lampasas County. Back during the war. Smallpox and Comanches took most of my family. Left my poor mother, my brothers and me. It's wide in the north, wide for the blockers. They were contracting herds on the Montana range. In the spring of the year '82, left old Lampasas with 2,000 steers.
That's why I see I'm a little confused with this whole V1 and Rn, because we have V1 on the left side also, but this is accurate, so I mean I'm just not fully understanding that, but anyways.
Not a bridge would we find in the cold rolling waters and the wild plunging cattle. There was many a young man took leave of his life.
V1 divided by V2, V1 divided by V2.
Well, we crossed it on
Well, I'm trying to figure out the voltage divider relationship, okay? Because now I just wrote it down, verbatim, whatever, however you want to describe that, and I want to understand it. So I'm looking deeper into this right here. It's a voltage divider, right? I think I figured it out. There's a voltage divider right here. So it's V2, V1 equals, where V2 is our input voltage, V2 multiplied by, what do we have? We have our two series, and we're going to have V1, so it's this series, or well, this portion of the series, which is Z1 parallel with Rn, and then that's in series, and the denominator with Z3. Yeah, that's accurate, that's true, and then we come to here. Okay. Okay, so we define this relationship between voltages What's happening here?
When I first
Why?
saw Montana,
V2 equals A1
I
V1
knew I would
equals.
love her. I would ride her great ranges till the end of my days.
What?
But she's all cut and dry, and the trails are all gone. I've been in the Yellowstone Park in an automobile, but I can still see 'em swimming.
Now we're back to
Boys, I
the
can
amplifier.
still hear 'em running. I came off of the trail when cowboys was king. My name is Bob Fudge.
Yeah.
I died in Montana.
V1 V2. Okay, I see the transformation, and then now we're going to say y V2 over A1 V1 equals. Alright, yeah, let's solve for this. But why is this what we're dividing by? V2. Oh, that's funky. Oh, because that's right, we take it back another time. Equals A1 V1, because that's our source voltage now, multiplied by that whole spiel. Right, because he's in parallel. Wait. Oh yeah, we got him in parallel with him now. Indeed. What the? Okay. That spiel. Z1. Z3. That's Z3. Z3. In parallel with this guy. Plus him. We want him, so. Yeah. What is that? Z4? That's Z4? Oh, Z2. Oh, Z2. Okay. I don't really got enough room here. No, I got it though. It's just the voltage divider relationship. I just didn't know how to divvy it up. You know what I mean? But I divvied it up now. Check this. Check this. Okay. V2 divided by. Oh, A1 V1. Okay, we can jump directly to this. That's right. I wrote in the same spot. Fuck. Alright, we'll jump to that. So we'll say V2 over A1 V1 equals. It'd be Z2 parallel with our series right here. Z1 parallel with Rn plus Z3. Now, is that accurate? That's accurate. Divided by this in addition to the series R out. Alright, right? Shit. There it is. Alright, okay, let's simplify it now. Like what? What they got going on here? What's going on here now? Z2. We got this fraction going on here. Just like that. Yeah. Yeah, Z2. Yeah, it's just the two impedances in parallel. Okay. So that's Z2 times. Divided by the addition of the two, right? Z2 plus. Yeah. What do we got going on here? Same thing plus R out. Okay. Okay. I'm seeing it now. It's all starting to make sense now. I hope you're rolling with me right now. It's all starting to make sense, so. Alright. Oh, man. Bang. Yeah, for sure. Okay. Cooking and I'm cooking. Okay. I'm following. So. Okay. Okay. Just why is it being... Because we're looking at Z3. This is Z3 represented here in feedback. And this is what we're looking across. Z3, this component. That's a component of interest. Component of greatest interest. Huh, okay. Very well, very well. Because we're looking at the change of this voltage. Yeah, this is the amplified, huh? Bang. Alright. Baby. Okay. Numbers, guys, something like that. Alright. Alright, we want to write it like this, I suppose. A1 times. Right, so we're gonna combine these. What's gonna happen here? going to assume that the input impedance is high. Very reasonable assumption to make, because the impedance at the base of the bipolar junction transistor, for instance, does tend to be very high. Okay. 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 Okay, how interesting. Alright. Okay. Wait, but still, this is what we simplify to. Because those go away. Is this correct? We multiply this here, r out times this, but wait a second, or well, no. No, this goes on top, that's on bottom, those are gone. Oh, so we do simply have that. Z2, this top function, the numerator of this fraction, and the numerator of this fraction make up our numerator and denominator, the whole fraction. Z1 Rn plus Z3. But yeah, now there's something here that we just discussed, or I guess we kind of learned together, right, as I'm learning this also. N plus Z3. Z3 plus R out. Yes. Okay. How's that looking on screen? That's okay. Can we see that? Alright. Okay. A1, Z2. So now. No. Right, now, this is the point at which we can neglect Rn, because I guess for our BJT transistor, the input impedance is very high. So it's an assumption that we can, well, yeah. Unless it's a MOSFET, then it's not such a good idea. But in this case, it's okay. And now we write that as, okay. Okay, very well. Alright, cool. So this. Do that. And so now we're going to solve for, okay. Ah, shit. Can you see that? Yeah, Z1 over. Now it's a voltage divider in terms of impedances, and we're looking at Z1. Why does Z1 come out on top? Why is that the impedance of interest now? Damn, it's still too bright, huh? Shit. Okay. And now what do we say about R out? I don't know that it remains. Let's see. Let's see. Oh yeah, them are the remains. Oh yeah, that's right, but we made that modification. Really? How is that so? Because of this. This multiplied by that. That's right. That's right. Okay. That's where that came from. Alright, fair. Fair. Where does this leave us? Let's see. Okay, we solve for this, and now we want to equivalate this to 1 for y. Okay. So now we're at this point. This goes, right? We cancel these. Z1, Z2, A1. I went to J times reactants. Let's see, it's an important property. Impedance of a reactive element. Impedance of a reactive element is J times the reaction when I write this equation. Damn. When element is active times reactance. Impedance of a reactive. Impedance of a reactive component. Impedance of a reactive component. Indeed, it's something active. Like in this case, I guess I was thinking something else, but yeah, reactive. Impedance of a reactive element. J times reactance when I write the equation. Z equals cool J. Where J is the imaginary part. I'm going to write real numbers in black, and I'm going to write complex numbers in purple. Not I. Okay. Okay. I see what's going on here. Okay. 1 equals. Yeah. JX2, and then we'll put A1 up here, divided by JX2 multiplied by JX1 plus JX3 plus, I guess, J R out X1 plus X2 plus X3. Yeah. Okay. Yeah, real terms and fake terms. Well, not real, I guess. Imaginary. I did it again. Oh, no. Yeah, negative x, 2x1 plus, well, minus So x2, x3. Damn, I should have did this x1, x2. Way better. Plus. Yeah, that's still imaginary. Let's see what. Okay, what do we. This term has 2j squared, blah blah blah. So, okay. Okay. Okay, therefore. Got one foot tapping in, nothing to lose or lost. I don't want to be found. Therefore, z1 plus z2 plus z3 plus z3 equals 0. Big fat. Oh, you can't see that. Big fat 0. Ah, shit, man. Oh, wait. There we go. That'll go. Yeah. Okay. Big fat 0. Yeah, that's totally. Oh. I don't know where my earbuds are. I think they're in the truck. Yeah. Okay, I just want to hear the sound quality. Alright, cool. Yeah. Yeah, let's get back to the speaker. Yeah, this is the derivation of everything. I guess this is kind of what I wanted, actually. Okay, so 1 equals, yep, okay, yeah, we figured all that. Okay, and that would indeed be 0. So we get this. Wait. Oh, okay. Okay. I'm just gonna do it as so noticeable, right? So negative x2, so negative x1 plus, or well, minus x3. Oh wait, well the negatives too, the. Yeah, hell yeah. What? What is this guy on, bro? On. Oh yeah, I'm missing some. We're solving for A. So x1, can you see that? Yeah. Oops. Yeah, what's Oh, cause okay. And we're all like x1, or well, we're solving for what? X2, we're solving for x2 equals x1, x2 equals x1 plus x3, yeah, that's just it. Because it equaled 0, well, minus. X3. And we had that. Okay, so x2 times negative. It was like that. Yeah. Like that. Therefore, we could call that x2. Yeah. Make another note here. Well, it looks like a division then. I'll just say implies x2. Wait, not negative though. That's the thing. Right. Is this not negative? Negative, it absolutely is. I gotta get back to the beginning, bro. Yeah, x2 j times j. Yeah, x2 x1 plus x3 and then plus, yeah, well, 0. So it's that. Yeah, we can cancel that. X1 plus x3 is negative x2. Yeah, negative x2. Okay. Using the property negative x2 equals x1 plus x3. Yeah. A1 would equal those are gone. Yeah, that is true. Okay, I'm on track. Let's go for some dubs in the chat, you know what I mean? Cool. Okay, we're defining oscillation conditions. Okay. Shit, I'm gonna need another page. I already used that page. I guess, new page. Should I rip it? Oh man, I don't really want to rip it, but it'd be worth it. Oh shit. Yeah, let's do it. We gotta be able to reference this one. Alright. Okay, so yeah, absolutely. A1. Let's redraw our circuit from the very beginning. So, okay. Yeah, we're doing this active element here. Reactive element. Maybe that's inaccurate to draw like that when we're doing the frequency response. I think I need to draw it as triangles. Yeah, bang. Shit. Yeah, but for the NPN transjunction bipolar transistor, fuck that. I don't know why that was so hard to say that time. For the NPN bipolar junction transistor, we're gonna have to model it as a current source, not a voltage source, such as the case right here with this motherfucker right here. But that ain't happening here. You heard? Alright. Man, I could totally use something to drink right now. Yeah. Alright. Continuing forward. Let's get on there. Gotta continue the theory on there. Oh wait, let's define these first. Z1, Z2. Oh yeah, we have to draw the other model too. Z2, Z3, Z1. Yeah. Yeah, that's the model we're basing it off of right now. It's like this. Okay, yeah, R out. V2. V1. Z1. No. Z3. Z1. Z2. Can we see this correlation here? Is this easy to see? Bang. Yeah, Z1. Bang. Z2. And Z3 is connected to... yeah. Okay, no, that's true. And then what? These are the same? Oh, shit. Wait, are these the same? That's RN. Yeah, because we got the feedback loop. A1, V1. V2, or V1. V2. Wait, right there? Yeah. V2. Okay. Ha! Ha! The delicacy by which this formula must be cared for. Grab the puny formula by the neck. Alright. So these are oscillating conditions. A1 equals x2 over x1 negative. Right, we defined that last time. Yeah, about all of this stuff that we did here. Okay, define that. Alright, we also define this by the property x2 plus x3 equals 0. Okay, and then now we know the properties that the reactance omega L or negative 1 over omega C, or for capacitors, C, 1 over omega C, yes, for capacitors. Okay. Indeed. Alright, now we're going to plug in and we're going to use the common emitter amplifier. Okay. Alright, now we're jumping to the full circuit. I guess we're just evaluating this. Okay. Alright. And we're going to use that. Oh, we just model the RC. Okay. So I'm drawing a common emitter amplifier and a with the LC tank feedback loop. How to... okay. That's how we'll draw it. Can you see that well? Heck yeah. Alright, cool. Do I like the way that it's drawn here? I kind of do. Alright, I'll follow this. Shit. Wait, nah. Nah, I don't like any of it. That's not even accurate. That's good though. Alright, cool, yeah. Hell yeah. C1, C2. Okay. What do? Nothing?
I might get to thinking that I might
VCC, VCC, VCC. We got a VCC. RG, RC, RV out, L3, C1. Okay, feedback, common emitter, amplifier. Bang!
This contemplation, this first conversation.
Yeah, let's do it all outside. I like it outside.
Feeling like that,
Bang,
talking to,
bang. What do we call this, C? Nothing.
I keep my hands working. It holds off the hurt,
Bang.
the work.
Oh,
Through,
I didn't do this circuit.
but when the days
Oh
end,
no.
then I'm on
I'm gonna move this.
Yes, but my mind wanders to,
I gotta move all of it.
and it's a feeling I've known since before I was grown. I'm howling, growling, the blues.
Man, this one's an electrolytic capacitor. I wonder why that is. Bang. 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 RERG. RG. CE. Yes. B out. Yep. RC.
And it's a feeling I've known since before I was grown. I'm howling,
Bang.
growling in the blues. I'm howling, growling the blues.
Cool. Hell yeah. Dang, shit looks right on camera, but it's kind of a little dark. Alright, okay, so we can further define, okay, derive A1. So, A1 equals, and we have this negative here, negative 1 divided by omega C1, we call it. What? Yeah. C2. 1 over omega C1. That's why it depends. The voltage gain depends on the capacitance ratio between C1 and C2. Okay. Now what do we got going on here? Negative plus. Okay. Using Kirchhoff's power law, or Kirchhoff's voltage law. Is that what just happened? I'm going to. Stars. Bang! Let's go. Oh man, that's too bad. So that's... Get started from the noise, right? That's the only thing, yeah, that would make sense. Well, considering that, what, yeah. What's going on here? What's going on here? What's going on here? Alright, enough messing around. I'm trying to understand what the hell just happened. Let's see. It's definitely a Kirchhoff's voltage law, but where is this being applied? I mean, within here? Ooh. I feel like it is, but like, a feeling, no. Unless... yeah, unless that was the case, or... Bro, like, what? Wait a second. Shit, bro, he doesn't specify. That doesn't make it. Oh, doesn't make any sense. Yeah, right. Okay. Okay. Hold on. I think I see what's happening here. Shit, maybe not. look, this is what happened. All right, here. Can you see that? Yeah. Okay, let me write it from the beginning. Alright, I'll be right back.
sometimes held up in the middle of the night, shaking like a pistol in a young man's hand there in the pale moonlight. Standing over top of that lonely hill, spared by the company mine, is my blue-eyed baby with a best dress on in the shadow of a long midnight. I was back before the war when the company came. These hills grew wild and free. Me and baby, we'd hide in the hollers, away from the cruel sun's heat. But then they knocked down the timber and burn off the brush to get to the ridges below. And when they pulled out, they left cold black ground and one pine standing alone. So take me home, One Pine Hill. Now I signed up back in '61. I'm an Army of Virginia man. I've been from Manassas to McConaughey, all the way to Sailors Creek.